In today's lecture, we'll finish talking about rational functions, and the main thing we still have to talk about is when we can simplify our rational functions because they have common factors. Now what this means is that if we completely factor the top and the bottom, the same terms appear and we can cancel them out. If we cancel them out and remove these factors from both the numerator and the denominator, it cancels out our zero and it cancels out our vertical asymptote, and instead it creates just a hole in the graph where nothing is defined. So let's see this in action. Let's graph x squared plus x minus 2 divided by x squared minus x minus 6. Now if we're claiming that these have factors in common, we better start by factoring them. X squared plus x minus 2 can be factored down to be x plus 2, x minus 1, and x squared minus x minus 6 can be factored down to be x plus 2, x minus 3, and we see we have the same term on top and bottom here. We have an x plus 2 and an x plus 2. By our rules of division, we can cancel these out and simplify our graph to just look like x minus 1 over x minus 3. And now we have no common factors. So this means that our complicated graph actually looks like this nice linear divided by a linear. And now we can start using our rules from before, but we need to be careful. If we simplify the denominator, the factor removed is still not in the domain. So if we state the domain of this function, it's all real numbers except x equals negative 2 from our simplified factor, and x equals 3 from the factor that still remains. Okay, so let's start using our rules here. We know we have a vertical asymptote at x minus 3 equals 0, or the point x equals 3. We know we have a horizontal asymptote at the line y is equal to 1 divided by 1. If we remember, this is because the degree on top and bottom is the same. So our horizontal asymptote is the leading coefficient of the top, which is 1, divided by the leading coefficient of the bottom, which is also 1. So this is simply the line y equals 1. And the zeros of our function we get by setting the top equal to 0, which gives us the point x equals 1. So let's do a quick side note here. Remember, asymptotes are always lines, and zeros are points. So even though the notation looks the same, this is a change we need to keep in our head. When we're doing asymptotes, we're always going to be drawing lines. And for zeros, we're always just going to be marking down points. So let's start graphing here. Here's our x-axis. Here's our y-axis. We have a vertical asymptote at x equals 3. So let's draw our brick wall in. We have our horizontal asymptote at y equals 1. So we'll draw in our tractor beam, or our cruise control here. And we have a 0 at x equals 1, which is right here. So actually, we know what the first part of our graph should look like. It has to pass through the x-axis right at our 0, and it'll have to home into the tractor beam. So since it never crosses the x-axis again, and the multiplicity of this 0 is 1, then that means it goes through the x-axis and has to decrease to negative infinity. It's not allowed to swerve back up, but we don't quite know what the graph looks like on the other side, so we do have to plug in a value bigger than 3. Maybe we'll do that in a little bit of a lighter blue here. All we need to do is plug in x equals 4 and see if it's above or below the horizontal asymptote. So if x equals 4, then we have our function x minus 1 divided by x minus 3 to plug into. So this is 4 minus 1 divided by 4 minus 3, which is equal to 3 over 1. So when x is equal to 4, y is equal to 3, and that means that we're above the horizontal asymptote, and again we'll sort of cruise control right into it, and we're done. We do need to make one small change though. Remember that we have this point that we threw out at -2 here. So we add in what we call a hole. So we say there's a hole at x equals -2, and we'll need to actually redraw this part here. We got a little bit optimistic. At x equals -2, which we can just say right here, we need the graph to not be defined. This means that the graph cruises right along like normal, but when we get to this one specific x value, it sort of disappears. And then once we get past it, it just keeps moving on like normal. So we've introduced a Bermuda triangle into our function. And we simply notify this by just drawing a hole at our hole. Now that that's in place, we have this graph done nice and easily. And we were able to use our rules since we simplified this function and got rid of the common factors. We can write out some guidelines for graphing rational functions. They're a bit long, so we'll go through them slowly and we'll highlight the important parts. Okay, so let's say we have f of x is equal to n of x divided by d of x, and d of x is not equal to 0. The first step is always factor and simplify if possible. Pull these apart into their base factors, and then if we have anything in common on top and bottom, throw them out. Remember, these points will be holes in our graph, and they are still removed from the domain. So even though they're gone from the function, they're still sort of invisibly there as holes that we just can't see and that we can't put down on the function. The next couple steps are just some nice simplifying things. We want to put a couple more points on the graph so that it's easier to find the picture. The first thing we can do is find the y-intercept by plugging in 0 for x, and then find the zeros of the numerator, and only the numerator, by setting n of x is equal to 0, factoring, and then we plot down our x-intercepts. This way we have a better idea of what the picture looks like and where we're going to be passing through the x and the y-axis. The next step is the real doozy. Step 4 is find the zeros of the denominator by setting the denominator d of x equal to 0, and then sketch the corresponding vertical asymptotes. So we just throw these brick walls in so that we can see what we're trying to avoid and what points we'll have to check. So these give us our vertical asymptotes. Once we've done that, then we should find and sketch the horizontal asymptotes by using those rules that we have for horizontal asymptotes, and we can use them since we simplified our function. Once the holes are in place, the y and the x-intercepts are in place, our brick walls and our tractor beams are down, then we just start plugging in points. Well, I use that color. How about I use this color? We start plugging in points, and we need to plug in at least one point between and one point beyond each x-intercept and vertical asymptote. If we look here, we knew that this function was going to hone in to our vertical asymptote right here. So we didn't need to really pick a point that was very close to 3. We could plug in 4 and just see, okay, am I above it or am I below it? If I'm above the horizontal asymptote, then I need to be going up to infinity, because I'm not really allowed to wiggle back and forth between this horizontal asymptote like crazy. Once I have all of these points in place, the last step is simple. We simply use smooth curves to complete the graph, and we draw some nice pictures like we did above. So let's try these 7 steps in motion here. And we'll do it by graphing f of x is equal to x squared minus 9 divided by x squared minus 2x minus 3. All right. Step 1. Factor the top and the bottom and see if we have any common factors. X squared minus 9 becomes x minus 3 times x plus 3. X squared minus 2x minus 3 becomes x minus 3, x plus 1. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. And we see we do have a common factor of x minus 3. So we will have a hole at x equals 3. And we're in motion. So now we consider the graph to simply be x plus 3 divided by x plus 1. And we start working with this. Okay. Step 2, plug in 0 for our function and see what our y-intercept is going to be. This is 0 plus 3 divided by 0 plus 1, which is 3 over 1, which is 3. Step 4, set the top equal to 0. And this gives us that we have a 0 at x equals negative 3. And now we have our 3 basic points for plotting. Once we have these, we need to add in our vertical and horizontal asymptotes. So let's do that. Okay. So we'll make one change here. There we go. Now, actual step 4, find the zeros of the denominator. This one's pretty easy. We have x plus 1 equals 0, which gives us x equals negative 1, is our vertical asymptote. Step 5, find our horizontal asymptotes. The degree of the numerator is 1. The highest exponent is 1. The degree of the denominator is also 1. So our rules say that we have a horizontal asymptote at the leading coefficient of the top divided by the leading coefficient of the bottom, which is simply 1. Step 6, we plot all these down, and then we pick some points between our vertical asymptotes and our 0 to see what it looks like. So let's actually graph this now. There we go. We'll try for maybe a straighter line in a second here. Less straight that time. One more chance. No luck today. Well, good enough. Okay. So let's plot some points down here. If we look up, we see we have a hole at x equals 3. So I'll just mark this for a hole, and we'll add that in later. Step 2 tells us we have a y-intercept of 3 right here. Step 3 tells us we have an x-intercept at -3 right here. Step 4 says we have a vertical asymptote at x equals -1. And step 5 says we have a horizontal asymptote at y equals 1 right here. And now we actually have enough pieces to graph this. We can see we have to cross through the x-axis at our 0, and we have to home in to our tractor beam of y equals 0. So the first half looks like this. The second half, we've plugged in a value that's past the vertical asymptote right here. It's above the horizontal asymptote, so it should look like this. And whoop, there's our hole. And there we go. So by using what we've learned in the previous sections, graphing these isn't too bad. If we had a couple more asymptotes, we might have to plug in a couple numbers. But we'll see that in some homework in some in-work class. The last thing we should discuss is what's known as a slant asymptote. Now, slant asymptotes are very specific. Let's say we have a rational function, and the degree of the numerator is exactly one higher than the degree of the denominator. If this is the case, then we have a slant asymptote, and we actually find this line by using long division. So here we see the graph of f of x is equal to x squared minus x divided by x plus 1. The degree of the top is 2. The degree of the bottom is 1. 2 is exactly 1 higher than 1, so it checks out. If we graph this, we'll see that our slant asymptote is the line x minus 2. And this is actually what happens if we do the division of x squared minus x divided by x plus 1. So let's work that out. If we turn this into long division, and we used our process, then we get x squared divided by x is 1x. And we multiply this x on both terms here, and get x squared plus x. Subtract it off. We have a 0 here. Minus x is minus 2x. And let's just add on a plus 0 since we'll need it in a second. Negative 2x divided by x is negative 2. This becomes minus 2x minus 2. Again, we subtract it off. We get 0. 0 minus negative 2 becomes plus 2. So x squared minus x over x plus 1 is equal to x minus 2 plus 2 divided by x plus 1, since this was our remainder here. And whatever term we get for our non-remainder is exactly the slant asymptote. So in these very specific cases, we have to do long division to simplify it a little bit more. But in general, these graphs are rather simple. So outside of the long division, they work exactly the same as before. But we'll just need to draw them a little bit more V-shaped and a little bit less U-shaped. As far as rational functions are concerned, though, this is all there is to talk about, and this is the end of the lecture.